Thank you very much for the opportunity to share with all of you some of the work that we are currently pursuing at CellSight. And for those of you that may not be familiar with CellSight, it is the Ocular Stem Cell and Regeneration Program at the Department of Ophthalmology at the University of Colorado. We launched this program in 2017 with the overarching goal of developing stem cell-based therapies to treat retinal degenerative diseases. And the most immediate goal we are currently pursuing is that of developing a retinal transplant derived from human-induced pluripotent stem cells to restore vision in patients affected by dry AMD. As most of you probably know, in patients affected by dry AMD, dysfunction of the RPE leads to degeneration of both RPE and photoreceptor cells. And so at CellSight, the approach we are pursuing involves developing a retinal transplant containing both photoreceptors and RPE cells organized as they normally are in the native human retina. And the hope is that upon transplantation, these cells will integrate into the host retina, regenerate these two tissues, and restore vision in these patients. And the foundation of our regenerative approach is the 3D retina tissue system that we established some years ago that allows us to generate retinal organoids that recreate the cytoarchitectural organization of the retina, including a nicely organized outer nuclear layer containing photoreceptors, rods, and the three types of cones, red, green, and blue cones. And very importantly, in our system, these photoreceptors reach a very advanced level of maturation to the point that they are capable of responding to light. And to complement this 3D human retinal tissue, we have also established a method to derive functionally mature RPE tissue directly from our retinal organoids. And as you can see here, this RPE tissue develops into the characteristic pigmented cobblestone moon layer. The cells express characteristic functional proteins, and they achieve advanced level of functional maturation, including transepithelial resistance, phagocytosis of photoreceptor outer segments, and polarized release of bioactive molecules like, for example, VEGF and PEDF. And so, having established these two complementary technologies, we have now established a strategy to bring these two tissues together to build a pre-assembled tissue patch containing these two cell types, photoreceptors and RPE cells, organized as they normally are in the retina. And what you can see here is an ortho-slice view of one of our retinal transplants, in which you can appreciate the RPE component of the transplant labeled in blue, and the photoreceptor sitting on top of the RPE labeled in green. And over here, this image is a close-up of a section of one of our retinal transplants, where again you can appreciate the outer nuclear layer with very nicely organized photoreceptors and the RPE and the underlying RPE tissue. And finally, we have recently initiated our proof of concept studies on the feasibility of transplanting these 3D retinal complexes using mini-pig models of macular degeneration. And what you see here is an image from one of our transplanted eyes, where you can appreciate the composition and organization of the transplant. Showing in green is the RPE component of the transplant, with the RPE cells labeled with human PML17. On top of the RPE, you can see the neural retina component of the transplant with the outer nuclear layer labeled in recovering. And you can also see here the remaining outer nuclear layer that is still present in the pig retina, sitting on top of the transplant. And so what I hope that you can appreciate from these images is the feasibility of transplanting these 3D complexes, the proper localization of the transplant in the target area, and nicely sitting underneath the pig retina. And so as an important component of this proof of concept studies, we have established a collaboration with our colleagues at Nanoscope Instruments to develop non-invasive imaging technologies to allow functional assessment at all critical phases of this process. Functional evaluation of retinal transplant before transplantation, functional evaluation of disease stage, and assessment of integration and visual function restoration after transplantation. And what I would like to share with you today is the development of a novel OCT-guided microfocal ERG system. This new technology is an integrated OCT electrophysiology system. The hardware is all packed into a portable system, making it very convenient for experimental settings, but also for its potential use in clinical settings. And in this picture over here, what you can see is the actual setup of the system in the operating room while we are working with one of our pigs. This system has the capability for standard B and C OCT scans. It also has the capability for standard full field ERG and a novel capability for ERG, that is the ability to perform focal light stimulation with different wavelengths, allowing for microfocal ERG of a specific photoreceptor types based on the wavelength that these photoreceptors are sensitive to. And finally, also a novel capability that allows ERG recording with single-cell and multi-cell resolution. And as a first step of validation of this technology, we evaluated the ability of this OCT-guided microfocal ERG to record light response from individual photoreceptor cells in wild-type pigs. Pigs have rods and two types of cones, blue and green cones, but they lack red cones. And what you see here represents recordings upon stimulation with a 450 nanometer wavelength to stimulate rods, which is labeled in blue, and with a 520 nanometer wavelength to stimulate green cones, which is labeled in green. The recordings were obtained at 3 predefined locations in the retina that were selected using the OCT imaging capability and using 2 very low intensities of light stimulation. And as you can see, there was no response from rods when using the lowest intensity of stimulation and a typical rod response when using the higher intensity. And the specificity of rod recording and the ability of the system to isolate rod responses from cone responses is demonstrated by the lack of response from green cones when using the same light intensities as those used to stimulate rods. And in addition to this, we were also able to validate the ability of the system to record light response separately from each one of the cone types present in the pig retina. So in this case, the blue waves correspond to ERG responses from blue cones upon stimulation with the 450 nanometer wavelength, but using a much higher intensity than those that were used to stimulate rods. And as you can see, the responses from blue cones are clearly isolated from the responses from green cones obtained with a 520 nanometer wavelength, again, at much higher intensities than those used in this case. And also almost complete lack of response upon stimulation with a 638 nanometer wavelength, which is consistent with the absence of red cones in the pig retina. And we further validated the specificity and sensitivity of the system by evaluating individual rod and cone responses in the P23 transgenic pig, which is a pig model of retinitis pigmentosa. So similar to patients with retinitis pigmentosa, these pigs develop retinal degeneration with initial loss of rods followed by degeneration of cones. So when these animals reach later stage of the disease, particularly in the visual streak, which is the equivalent of the human macula, what you see is a single row of photoreceptors that are remaining in the retina. These photoreceptors correspond to cones and a complete lack of rods. And so consistent with this, as you can see, we detected a complete lack of response
Yeah.
in rods using the same conditions that
No,
we
I
use
I'm
in the
here.
retinal,
So if you
and
click on
minimal
the sheet two
responses
of this,
from green and blue cones.
yeah. So yeah, I have uploaded
And
those.
so, as I
So the rest
mentioned
of them I'm
earlier in the
unable to
presentation,
find it.
our
So
goal
you
is to
can,
establish this
if you have
technology
any.
as a theranostic platform for stem cell-based therapies for retinal degenerative diseases, and the
I wanted
portability
to change
and
the color, but I
ease
didn't
of
want
use
to
combined
do
with
it
the
without your knowledge.
versatility
So
of the
that's why I put it as
system
a key.
makes it an ideal
So,
platform for achieving this goal. So we are currently adapting the system and establishing
yeah,
the
I have put it
correct
under the
parameters
procedures
for its
in
use
the
in
procedure
vivo,
folder.
and the intention is to use it for functional evaluation of our retinal transplants prior to transplantation, with the intention of using it for both the preclinical product and eventually the
Yeah, I'm
clinical
unable to
product.
find any more. Try to look.
We are already using the system within the context of our preclinical studies
Yes.
for assessment of the retinal function prior to transplantation, and we also
Okay.
anticipate its potential deployment to the clinic in the future for diagnosis and evaluation of disease progression in patients. And finally, a very useful capability in the context of our preclinical studies, which is the ability to detect ERG responses for each type of photoreceptor cell separately, and based in the fact that the pig retina lacks red cones, but red cones are present in our retinal transplants, we anticipate that it will give us the opportunity for the first time to specifically differentiate light response from transplanted photoreceptors versus host photoreceptors. And finally, I would like to acknowledge everyone contributing to the project, everyone in my team who has been significantly contributing to the results that I have shared with you today. Dr. Mark Matthias, the vitreoretinal surgeon responsible for the surgeries in the pig, everyone in the CellSign team, and very especially the Nanoscope team. It's been an amazing collaboration, and I do look forward to many more years of working together.